What you are seeing here is a chemical reaction, a mixture of chemicals reacting together to give products. And as they do so, we observe an effect. In this case, movement of this drop of liquid metal, mercury. When we observe chemical reactions, we look for changes. Here we see colour changes. In some reactions, a gas is given off. Sometimes we see a change of form or production of heat or a loud noise. The explosion of a hydrogen balloon is clearly a chemical reaction. Now the reaction occurs very quickly, and in fact we have to slow the film down for you to see the full effect. But not all reactions are quite so obvious. There are many reactions that go on underneath our noses and yet we can't see them. One of the reasons for this is because some reactions are very slow. Take, for example, rusting. If I look carefully, I can't see rusting going on, but I know that rusting has taken place because originally this metal plate was clean. Another reason why we might not see reaction is because there may not be a physical change. Have a look at this reaction. There, reaction has occurred. Did you see it? If I were to analyse the reaction mixture, I could show that reactants had been converted to products. What I want you to do now is to watch the following reactions and write down in your study file what changes are taking place. Here we bubble oxygen through the solution. The lights are deliberately dimmed. As oxygen was bubbled through the solution, it changed colour from yellow to red to green. On removing the oxygen, it went back again to red and then yellow. These reactions give out light. These reactions involved a colour change again, first to orange, then black. In the other flask, it occurred more slowly. When a chemical reaction takes place, we not only get the conversion of reactants to products, there are also energy changes. Energy is either released or taken in. Take a look at this reaction. Here I've got two reactants. The temperature of one reactant is about 18 degrees, 19 degrees Celsius, and the temperature of the other reactant is again about 18 degrees Celsius. Now, when I mix these two, a chemical reaction occurs. And the chemical reaction gives out energy, and that causes the solution to warm up. So now when I measure the temperature, it's up at 65, 64 degrees Celsius. When I mixed the reactants, I got a chemical reaction that gave out energy, and the energy caused the temperature of the solution to rise. But are there other forms of energy change associated with reactions? Take a look at this series of reactions and write down in your study file what energy changes are taking place. Again, the room is darkened. Here we measure the temperature of the reactants and products. In this reaction, we have a coil of copper wire. The pot contains another solution. The electric motor of the fan is connected to a piece of aluminium and to the copper coil. The reactants here are two solids. As the two solids react, they form a liquid. Energy was given out in this reaction as light. However, little heat was generated. The temperature of the solutions was the same. This reaction generated electricity. The reaction gives off a gas. When the coil was removed from the solution, the reaction stops, and so does the fan. When the two solids reacted together, they absorbed energy, and the temperature of the mixture dropped to minus 20 degrees Celsius. The water on the watch glass froze. One of the reactions gave out light for about 5 seconds or so. Now I can do a similar reaction here in the studio using a commercial light stick and expect to get more light for my money. When I bend the tube, a vessel inside breaks and releases chemicals and causes a chemical reaction that gives out light. And if we dim the studio lights, I think you can see just how much light this gives out. But not all chemical reactions involve the release of energy. Some reactions absorb energy. As you saw, when we mixed two solids which were at room temperature, the temperature of the solution that we formed dropped to minus 20 degrees Celsius. That's a change in temperature of 40 degrees. Of course, not all reactions involve such a dramatic change in energy. Sometimes the energy change is quite small. But the important thing to remember is that the vast majority of reactions involve some kind of energy change. Take a look at this next reaction. It involves heating ammonium dichromate, an orange crystalline solid. In this reaction, ammonium dichromate reacts to give chromium oxide, nitrogen and water. At the beginning of the reaction, we've only got our reactants. At the end, there's only products. There are no reactants left. We say the reaction has gone to completion. Another important aspect of these reactions is that they only go one way. I can take my ammonium dichromate and react it to give chromium oxide, nitrogen and water. But I can't take this chromium oxide and react it with nitrogen and water and expect to get ammonium dichromate. We say the reaction is essentially irreversible. But not all reactions are irreversible. Here I've got some cabbage juice. It contains a red compound. If I add base to this red compound, it goes green. My red reactant has been converted into a green product. Let's see what happens if we add acid to this. It goes red again, and that looks suspiciously like the red compound we started off with. Let's see what happens if we add base to this. Sure enough, it goes green again. What we've got here is a reversible reaction. We've got a red compound that can be converted to the green compound by addition of base. If we add acid, the reaction goes back to give the red compound again. One of the interesting things about reversible reactions is you don't have to have just the reactants or the products. You can have a mixture of both. If I add just the right amount of acid, I can get a purple colour. This purple solution contains roughly equal amounts of our red reactant and green product. And if I add this to acid, it goes over to our red compound, and if I add it to base, it'll give the green compound. So I've got the red reactant and the green product and a purple solution, which is a mixture of the red and green compound. Now let's look at another reversible reaction. It involves the conversion of a pink reactant to a blue product. The conditions can be adjusted so that the mixture contains equal amounts of the pink reactant and blue product to give a violet-coloured solution. In the following experiments, use these colours to identify what substances or mixtures we start and finish with. In particular, write down in your study file what changes occur and what may cause them. a beaker of boiling water and a beaker of ice. We started off with a violet solution containing equal amounts of the reactant and product. When the violet solution was placed in boiling water and heated, it became blue, as all the reactant was converted into product. On cooling, the violet solution went pink, as the product was converted back to reactant. When we swapped the solutions over, the pink solution warmed up and slowly became blue. Whereas on cooling the blue solution, it changed back to pink. Most of the reactions we've seen so far happen instantaneously. For example, when I added the base to the red compound from cabbage, it instantly went green. Have a look at this reaction. It's a slow reaction. Nothing much seems to happen at first, but the reaction carries on until it reaches a critical point and then goes blue. And the time taken for the blue colour to appear reflects how fast the reaction occurs. Watch the following set of reactions. As we go from left to right across the screen, the concentration of both of the reactants decreases. Using the clock on the screen, time the colour changes in each beaker, and thus decide how the concentration affects the time taken for the reaction to progress to the stage when the colour change occurs. Remember, the beakers on the left contain the highest concentration of reactants, whereas those on the right contain the lowest concentration of reactants. The higher the initial concentration, the faster the reaction. The speed of the reaction also depends upon the temperature. Here I've got two identical reactions containing the same concentration of reactants. The reaction on the left seems to go faster than the reaction on the right. Why is this? Well, the reaction on the left has a higher temperature. Than the reaction on the right. And this is true for most reactions. The higher the temperature, the faster the reaction. Some reactions occur quite slowly if left to their own devices, but they can be speeded up by the addition of a small amount of a compound known as a catalyst. This orange-coloured solution is the final product of a reaction between hydrogen peroxide and this violet-coloured solution. Although we get a colour change, it takes about an hour or so before it finally reaches the end product, the orange-coloured solution. But I can speed this process up. If I first add a catalyst to the violet-coloured solution, and add the hydrogen peroxide, the reaction still takes a little time, but it does occur much more quickly. Hydrogen peroxide, the stuff you can bleach your hair with, is fairly stable. It doesn't break down to give oxygen and water. However, when we add a small amount of catalyst, it's altogether a different story. In a violent reaction, the hydrogen peroxide produces enough gas to fill this gas jar. Applying a glowing splint confirms that the gas is oxygen. Catalysts can come from unpredictable sources. For this reaction, they include liver and potato. Washing up liquid is used as a marker for the reaction, as it will produce foam as any gas is given off. Now for our catalysts. We have iron oxide, potato, liver, manganese dioxide and lead oxide. Adding hydrogen peroxide to the cylinder on the right, pouring produces a little foam, but no gas is produced. This is a poor catalyst. Now for the rest. We can see which of our catalysts is best at speeding up the decomposition of hydrogen peroxide to oxygen by the amount of foam produced and the speed at which the foam reaches the top of the cylinders. Lead oxide is the best catalyst, followed closely by manganese dioxide. In the second flask, you can see the black manganese dioxide still present in the foam. This reflects one of the key properties of a catalyst. It is not consumed during the reaction. The next best catalyst is liver. Gas continues to be produced at a steady pace. The potato produces some gas, but it is a poor catalyst. The foam relights the glowing splint, confirming oxygen is produced. We've seen that chemical reactions involve a change in energy. Some reactions are essentially irreversible, whereas others are reversible. We've also seen that chemical reactions can occur at different speeds. It's important to realise that the speed of a chemical reaction has nothing to do with whether it's irreversible or reversible. You should now return to the main text, which explains some of the theory behind the practical observations you've made in this video.